There's a couple of pictures here, one of ballasted track, one of non-ballasted track, just by way of introduction. Those pictures are actually taken only a few hundred metres apart, and they show that you can use either on the same project. The particular point I wanted to make here, though, was not why you would choose one or the other. You might get a hint as to that from the fact that one's in a tunnel and one isn't. But the thing is, if you take away the ballast from the system, you lose a number of aspects of the performance of the system. So one is a degree of resilience, which the ballast provides. Another one is some drainage. And the third one would be the capacity to make adjustments to the line and level by tamping the track. So the way that you overcome those losses, at least one way of doing that, is by providing that capability in the fastening system, which tends to mean you have a slightly more complicated fastening system than on ballasted track, typically a baseplate arrangement. So if we look at, for example, if you were to look on our website, a bit of advertising there, but you would find that we supply quite a few different designs of baseplate. So why would you choose one over the other? And probably a good way of looking at this is to look at the kind of things that are important to you as a user or our customers. These are the kind of things that we get asked questions about. So what you might then do is look at your own particular project and assess how any given baseplate performs in relation to those different criteria. What I particularly want to do, though, is focus on just one design of baseplate because it's a good all-rounder. It actually performs quite well in relation to all those aspects. So it provides quite a good framework for talking about all of them. So what I basically want to do is work my way through that list and talk a little bit about each aspect of the performance of the track of the baseplate. And I'll either reach the end or I'll get shown the red card if I carry on too long and we won't reach the end. But hopefully we'll get there. So if I start off by talking about the stiffness and design, a baseplate like this is clearly it's made up of a large number of components, but from the end user point of view, you don't really have to concern yourself with that because most of it is pre-assembled into one unit and some anchor bolts to fix it down. So you can treat it as one unit. From the kind of technical point of view, that's defined as an indirect fastening system. And the reason for that is that the means of fixing the rail to the baseplate and the baseplate to the slab are separate and independent from each other. So there are two different mechanisms there. Other aspects of this kind of design, the rail is mechanically and electrically isolated from the baseplate, and the baseplate is the same to the slab. And then you've got two pads in series which can be independently configured. So overall, that gives you quite a lot of flexibility in exactly how you configure this kind of system to meet any given requirement. So just to, you have to watch this quite carefully and quickly. It goes, but these are the key aspects of the system. So the base plate and the anchor, the fastening of the rail to the base plate, and then you've got two pads in series. So that's what we're looking at. Now, typically, you would be looking to design for low mechanical stiffness and high electrical resistance with two elements in series. Looks kind of similar. And in fact, the equations that govern those systems are pretty similar, but the thing to notice here is if you apply a force to the base plate, it will be transmitted through the base plate into the slab, so it's the force that goes through the whole system. If you apply an electromotive force, i.e. a voltage to the rail, it's actually the current that goes through the whole system. So if you look at the equations for those two things in series, quite rather neatly, two springs in series give you a lower mechanical stiffness than either one, whereas two resistors in series give you a higher resistor resistance than either one, which is what you really want to achieve. So if we look at the simple case of electrical resistance, you've got two layers, one on top of the other. You've got two levels of resistance for current to get through. If you look at the mechanical aspect, the key things to notice here are that you can achieve all sorts of different levels of stiffness by choosing appropriate pads. So as represented by the different colours, you can choose different overall stiffness levels. But also for any given stiffness level, you can achieve that in many different ways by different combinations of pads. And that's something I'll come back to later because that's a kind of useful aspect of the system. So how do you then use these kind of systems? If we look at transitions, there's a picture there of a transition between slab and ballast, and actually not very much has been done there. You go straight from one to the other. So there's an extract from a paper from about 20 years ago that's pointing out why that kind of arrangement might lead to problems. So on the left-hand side, you've got relatively soft track with a large deflection, a large bowl of deflection. As you move towards the right-hand side, the track stiffens. And that gives rise to, first of all, dynamic forces as you transition. And that can then lead to settlement, and you can get into a kind of spiral of deterioration. So the worse the settlement, the bigger the dynamic forces, the worse it settles. So to overcome that kind of problem, you might well want to do something along these kind of lines to design some kind of smoother transition between one type of track and the other. And the way we would approach doing that is to use our own bit of internal finite element software, which just allows us to configure different configurations of base plates, spacing, rail sections. And you can see the top trace there looks like the deflection bowl from the previous slide, and the bottom trace shows how that deflection bowl changes as you move along the track. So in fact there we're going from stiff track to soft track and back to stiff track again. So if we look at an example of how that's been put into practice, this is an example from the Øresund link between Sweden and Denmark, which was actually built nearly 20 years ago now. There were sections of that which were slab track with booted blocks in it, and other sections which were ballasted track. And there's a story actually that the border between Sweden and Denmark exactly corresponds between the difference between the slab, and I don't know if that's true, but at any rate, it did create a problem. So that after 3 or 4 years, the system was not working very well. It was deteriorating quite quickly, and you were getting that settlement. We were asked to see if we could help propose a solution. So we went along and made some measurements, determined the exact stiffnesses that apply in the tunnel there. And then we were able to use the software to predict different scenarios, what would happen if we put different combinations of base plates in. And then we were able to use that capability of changing the stiffnesses to generate different stiffness levels in the base plate. So a couple of years passed, and eventually that got installed in the track, and here's a composite picture showing roughly what that looked like. So essentially on the right you've got slab track, on the left you've got plain line ballasted track, and in between there are bearers of different lengths with base plates of different stiffness have been installed. There's also a couple of extra rails being put in the middle to transfer shear loads from one side of the transition to the other, which are fixed with much stiffer base plates. Few pictures of details of that arrangement. One of the key things with this kind of thing is to make sure that it's clearly identified what is supposed to be where. You've got to think about the scenario when in a few years' time somebody takes the whole lot apart and then has no idea how to put it back together again. So what we've done here is to colour code all the elements so that there's some kind of clarity about what is supposed to go where. Taking that further forward, the LGVS line in France, the high-speed line, was mainly based on ballasted track, but there are a few sections of slab track there. There was a deliberate design there for transitions between slab and ballast, but it didn't work very well. And a couple of years later, SNCF started talking to us again about what could be done to improve the situation. We explained what we'd done on the Øresund link, and they took up that idea, asked us to configure a couple of particular specifications of base plate. And that situation, that configuration was again installed in the track. That was done about 5 years ago. So that's on extremely high speed track. A picture in the bottom right-hand corner shows quite a foreshortened view of it. So overall, it's probably about 20 meters long. But that's been in place for about 7 or 8 years. No, 5 or 6 years now. It's working quite well. Next issue, track structure and interaction. So just to give you a flavour of this, suppose you've got a really long structure which can expand and contract, but you've got a continuous rail running over the top of it. That's going to give rise to problems because the expansion and contraction of the structure is going to reflect in the rail and is going to induce stress in the rail. Now, one answer to that would be to put a joint in the rail as well. But you really want to avoid doing that if you possibly can because it generates more maintenance issues. So looking at a couple of extremes, and these are kind of ludicrous extremes, if you were to weld the rail to the bridge deck and the abutment, you would focus all that expansion and contraction on just one span. So that wouldn't be a very good idea. You get a huge amount of expansion and contraction in just one span. If you did the other extreme and you mounted the whole thing on a resilient, longitudinally slippy fastening, this is an arrangement we've got for de-stressing, so you can raise the rail up, there's no resistance at all. The problem there would be what happens if the rail breaks in cold weather. It's going to pull a long way apart. So you don't want to do either of those things. You want to do something in between. And to understand exactly what it is in between that you need to do, again, you would probably look at some kind of model of the system. So this is the one we use. You can set up different models of the track, the vehicles, the temperature gradient, and you can look at different situations where the train is on the bridge, work out the biggest stresses. And then the other aspect to addressing this kind of problem is actually having something to do at the end of it. You know, how are you actually going to fix the problem? So what we've got here is a standard configuration of the base plate into which you can swap a low toe load clip, so that will give you less resistance, or a step further than that, you can have a clip with no toe load at all. It's not actually acting on the rail, so you get no resistance at all. You can still maintain the track. And in fact, you can also configure that to provide uplift resistance. So at the end of structures, typically where you get these problems, you also may get rotation of the bridge and the rail. So you want a bit of resistance there. So those kind of modifications to the basic system can be applied. Here's another kind of example. This again from the LGV Est in France. The middle picture shows that in this instance, this structure is so long that they have had to put an expansion joint into the rail, but actually that wasn't coincident with the structure joint. So there's a short piece of track where the rail's moving, but the bridge isn't. And that you can see the effect that's had on the toe insulator of the clip there. It's a relatively minor problem, but we can eliminate that by putting zero toe load clips over that short length of track. So another picture here, again from, this is a high-speed line in Korea. There's an inset picture showing my colleague has slipped his business card under the toe just to show there's no contact there at all. And if you've got very good eyesight, you can probably just about make out that in the foreground you've got blue toe insulators, so those are zero resistance. Further away you've got white toe insulators with full toe load. So you can tell from that picture actually that you are standing somewhere near the joint and looking away from it. Next issue, noise. It's really quite a complicated subject, so if you'll excuse me with a very, very brief and superficial explanation. Fundamentally, it's quite a good thing to have soft fasteners immediately under the wheel. It reduces the amount of transmitted vibration and it reduces wheel-rail contact forces. But when you get further away from the wheel, it's quite a bad thing to have a low stiffness fastener because it means more transmission of vibration along the rail. So you've got a kind of basic conflict of interest there. And what can you do about it? Well, this is a kind of neat idea, which we didn't invent, but we did realise it worked quite well in this kind of system. So we've got a test rig here, which is basically a small part of one of these base plates with the anchor mechanism. And we can set that up and then apply an external load to it. And what you find is the external load gradually replaces pre-compression supplied by the anchor system. So actually you don't get a big change in deflection even despite applying a large load, which actually translates to being a high stiffness. So if we compare a couple of configurations here, one with pre-compression, one without, you can see that the effect of adding pre-compression to the pad is that you can make it behave as though it's stiff at low loads and soft at high loads, which is exactly what you are trying to achieve to get a good combination of vibration transmission mitigation under the wheel and lower noise away from the wheels. So to figure out if that actually works in practice, you really need to do some laboratory measurements, you need to do some predictions. That's all kind of quite specialised knowledge. So we've been working with ISVR in Southampton on that. The first step in the process is to measure in their dynamic test rig the characteristics of the assemblies. So you can do that, and this kind of plot, if you're used to looking at things like this, you would probably assume that's frequency along the bottom. In this instance, it isn't, it's load. So that the blue line actually represents an assembly that is getting a little bit softer as you put more load onto it. So that's what we're looking for in this test rig. The next thing would then be to make a prediction of the track decay rate, which ISVR can do. But in fact, even better than making a prediction would be if you could measure that directly. And normally that's quite a difficult thing to do on a live railway, because you need to attach all sorts of instruments, you need to spend a lot of time tapping the rail with hammers, you need to change the configuration to all the arrangements you want to test. But at the High Speed College in Doncaster, there's a fantastic thing. It's even got a nice roof on it to keep you dry. So you can test away to your heart's content, change all the configurations and confirm that decay rate prediction. And then you can make a noise prediction from that. And what that shows is that you actually are predicting different noise levels for 4 different configurations of the assembly. Now, I've seen graphs like that before, but the special thing about this is that they've all got the same stiffness. So you're changing the noise level despite having the same stiffness in all those configurations, which is kind of neat. Next up, ease of adjustment. So here's that picture of slab track again. You can see now that it's built, in this case, from 5-meter slab panels. So that's all great on a straight piece of track, but if you go around a curve, you're going to get what the older members of the audience will recognise as a threepenny bit problem. So you're going to have to offset the base plates on each slab to produce a perfect curve. And actually, there's a bit more to it than that, because you really want the base plates not to be perpendicular to the slab, but be to pointing to the middle of the radius. So you want the base plates to be in particular positions and configurations on the slab. And there are conventional ways of doing that. One involves making bespoke slabs to which you can then fit universal fasteners. The problem with that is if you then damage a slab, you need to go and make an exact replacement for what you've damaged. You can have a universal slab and make adjustments within the fastening system by changing components, but that's not great because then you've created a bit of an ongoing maintenance problem. So what we propose is you have a universal fastener and a universal slab, and you put the fastener in exactly the right position. And that's in principle the best solution, but you need a slick means of positioning those base plates in exactly the right places. So we proposed about a year ago that we could do this by borrowing the manufacturing technology we use in our factories for making clips and applying it to this situation. So robots can be programmed to go to exact locations and put the base plates where they need to go. So since then we've been working on that, and we've now got a fairly well-working prototype of that, which is picking up base plates, putting them on the slab, holding them in exact position until they're bolted down. So you can repeat that process, and it will take about 6 minutes to fit all the base plates on one slab. Now, you can really only do that because it's quite an easy system to adjust. You don't need to swap out lots of components in order to make positional adjustments. And to demonstrate that, we've got a little video clip here. We kind of challenged one of our technicians to do the job of making an adjustment one-handed. He didn't quite manage that, but he did a fairly good job of it. So this takes about 40 seconds to run through. So basically what he's doing here is lifting up the base plate by 15 millimeters. Now, what you'll often find is if the slab is inclined, that's going to have an effect on gauge as well. So not only do you need to make a vertical adjustment, you need to make a lateral compensating adjustment as well in order to retain gauge. So he's doing both those things at the same time. And he's almost at the end now. What we've done here is we've put a red laser on the face there, so you can probably just about see that's what he's setting it to. Now, you can provide instructions on how to do that. It's fairly simple, but the modern way of doing this kind of thing is probably to encapsulate all that information, so all the information about the product and the way that you maintain it in BIM files. So that's perfectly possible as well. You store that knowledge about how to make adjustments in the BIM file, and that's part of the overall design. If we look at range of adjustment, why would that be important? Well, this is a picture from Taiwan. It's not this particular base plate, but it is a base plate on a high-speed line. And what's happened here is there have been some seismic activity, so the track has dropped locally, and it's been adjusted back up. So you can keep the track open, running at full line speed by making that adjustment. To do that, you need quite a large range of adjustment capability. And you can provide that with this kind of baseplate system. What we did is really kind of went to town on this and put 140 millimetres, which is double the amount that we've ever heard specified before, but we thought we'd prove that you could do it. So on the left there's a baseplate that's been adjusted upwards by 70 millimetres. On the right, it's been adjusted up by 140 millimetres. We've actually run that for 3 million cycles, a standard European durability test, and it works really well. Another factor is ease of maintenance. So this is, again, something that's important to users. Again, we've got a video clip here just showing the capability of this type of system, that you can apply the clips very quickly. About 70 sleepers a minute is the capacity. And you can take them off as well at a similar sort of speed. So you've got a lot of capability there. That was, I don't have a slick video of it, but you can apply the same kind of technique to base-plated systems on non-ballasted track. This is a machine actually being used to do exactly that. I think this is the Heathrow Terminal 5 extension. Base plates being fitted with a machine of that nature. And another aspect to it is that you can inspect your track by video. The position of the clip is fairly easy to detect, so you can tell whether it's been installed or backed off just by looking at it. So you can do that in principle by running a train down the track at fairly high speeds. You can get up to 200 kilometres an hour and continuously monitor every single fastening. So this is some work being done on China on developing a particular configuration of exactly that kind of system. So I have actually reached the end. There's one label there that I'm not going to talk about, cost. I mean, this is a technical conference, but the cost, rest assured, is this kind of base plate is pretty competitive. So that's it. Thanks very much.